Yes, sir. It says you're recording, yes. Yes, sir. I'll ping you once the class is done. Uh, Babu sir, I think we can get started.
Okay, fine, we do that. Okay, so good morning to all. I'm Babu Narayanan from CVIT, Center of Excellence in Wireless Technology, IIT Madras. The idea is to cover some of the overall aspects of 5G in the next 2-3 sessions, 2-3 classes. I'll use a set of presentation slides, and as we go, I'll also try to explain using whichever mode I can draw it or annotate and add to the slides information. So let me first share the slide. Can you see the slide?
Yes, yes.
Yeah, okay, fine. I have put in the presentation mode. So the idea is to cover these two topics mentioned here in a very broad level, the 5G architectures and some extra focus or what is meant by 5G core. So you'll take it as two different or across multiple sessions. My idea is to cover the first one, the 5G architectures today. And if time permits, we'll get into a little bit of 5G core. So what we plan for today is to look at the various subsystems and the components that form a complete 5G network. This may not be totally unfamiliar to you, but I thought you can start with some basics. Some of you may not be fully aware, some of you may be aware of the complete thing. I'll just run through the basic components that that makes up the complete network, and as we see in a typical cellular network. Then we look at some very basic concepts and also some standard interfaces that is defined in 5G that would be of interest as a 5G technology itself. Then we look at two interesting aspects again from the 5G point of view and from evolution to 5G point of view. One is the architectures in RAN, the way 5G RAN architecture is evolving. And then we also look at what the migration path from 4G to 5G, which will again be of interest because that's something which we'll see in the market in the immediate future. And as I said, time permits, we'll get into 5G core today, or we can start it in the next class. So starting from just to understand, just to look at the very basics of what is network made up of. I think all of you are aware what is a UE. I think this term is now much familiar with it. This is user equipment which is same as your handset or a device or a modem that is on any of the embedded systems. Basically, this is the one which initiates or which wants to connect to the larger network. It can be a CP, consumer the premises, customer premises equipment. So there are various forms of this UE, and the most common one is what we see as a handset in our hands, which transmit over the radio technology to the what we call as a base station. Sorry. And the base station has different names. In 5G, it is called G node B. Again, all of you are quite familiar with it. And the base station is connected over a transport network to what is called a core. And from the core, it is connected to the external network, the data network. And that data network can be of multiple kinds. It could be just the internet, it could be the operator's intranet, or be some other enterprises intranet, and so on. Basically, what is happening is the UE get connected to the data network through the base station and core. So you can see that the network as such is made up of a base station and a core, two major components. And of course, UE is also part of it as a user device to look at it. And this is what we call as a 5G, which what 5G specifications technology influences are these three parts. The UE technologies, how the UE is designed, how the base station is designed, and how the core is designed. This is the data network is outside the scope of the 5G, but of course that is required to connect to the external servers. You may have all the servers, your internet servers, IMS servers, you all can be here. You can also indicate IMS separately. IMS is by itself a subsystem which is provided by the operator. IMS is primarily used for, in our current situation, it is used for voltage in 4G, and in which future will be used for voice over NR, basically for voice video purposes, multimedia purpose, we use the IMS subsystem. So there is a large set of servers with a specific responsibilities and role as part of the IMS, and core connects to the IMS. And the UE, in fact, connect to the IMS just like to the internet through all the base station core and the to the transport network. I think I should also mention this very clearly that transport network is what comes in here. It's just a line, but it's a huge network of transport from the base station towards the core. Base station could be located very near to the towers, which are very near to the user, and the core could be hundreds and thousands of kilometers away. So this transport network sometimes plays a very big role in actual performance of the overall system, especially when we come to 5G where latency is important. This gets additional importance. It's also important from the capacity point of view. When you have multiple base stations, for example, you have several UEs connected to several base stations. You have tens of thousands of UEs connected to base stations, and all the base stations are connected to the core. So this transport network becomes very important in terms of how much it can carry the total capacity of this thing. could be in terms of tens, and in future will be several tens of near to 100 Gbps. So that's very important in terms of how the transport design. Many a time when we discuss 5G technology, because this is outside the scope of 3GPP and the pure 5G as such, it has to be handled separately.
So how many G-Node pieces can be connected to core, sir?
There is no specific limit as such. There can be hundreds which cannot be connected to the core. And if you look at the typical network architecture that you would see, it could be one core handling one circle or a PLM, and we call it here. And one circle 7 is a Tamil Nadu circle or a Karnataka circle. And sometimes there can be a core supporting multiple circles. So that is a level of the coverage or the kind of domain of the core. Whereas a base station is only, if you would see like a base station is sometimes just 200 meters apart in an urban area. In the case of rural areas, it could be in terms of a few kilometers. So there are hundreds of base stations in a city, and they all have to be connected from city, rural villages, all connected to the same core. There is a large number of hundreds of base stations that connected to a core as such. And if you see again, the architecture in 5G is slightly going to be different. What you see here is more some kind of a monolithic fixed architecture. The kind of architecture that is being now looked at in 5G is much more flexible. So we'll come to that later in the sessions. So,
Excuse me, sir.
Sure.
Sir, how do you understand a G-Node B? I mean, do you imagine it? I mean, do you visualize it as a cell tower, or what? How do you exactly understand it?
Okay, very good question. Yeah, again, I'll come to that details later. But you can say it is not just a cell tower; it's all the electronics and components and software that kind of communicates to the user interface and also communicates to the core. All the functionality that are in between becomes a base station. So it is not just a single piece or a box. There are many pieces that come in, including from antenna level to the, see, for example, the first entry is from antenna level here. And what goes out is to the transport network, some data that is on the protocol towards the core. So from, from the antenna to this thing, whatever is contained inside in terms of the electronics, your FPGAs, your baseband boards, server boards, all the stacks that go inside is, all this become part of the base station. So base station, as I said, don't think it as one, even though it's a logically one role, it is actually made up of multiple pieces, boxes.
Right.
Yeah.
Thank you.
Yeah. And in order to understand from the operator viewpoint, maybe you can also look at, there is another layer altogether over this, which is a management layer. So management layer is something which we don't look at from a technical point of view, because that's dealt in a very different domain and protocols, and it's more the IT domain. I can maybe put it as an IT domain, not the engineering domain. So much of the management has been in terms of the operation support, business support. Then you have all the element management, network management, and so on. So they all get connected to the individual network components in some protocol form, and they capture the information, they influence, they configure the base station. If you want to configure base station, it's a management involved. Similarly, configuring the core, management is involved. In configuring the transport, there is a involvement of management. So management has the overall outlook, and it is through management that actually the operator teams, including the network operations center or the overall management of the network, is done. But we will not cover those. That's a huge another area by itself, which are not so much related to the 5G technology also. Even though you will see that again, as the 5G has evolved, especially from the core point of view with the new technologies like we have SDN, virtualization on, what happens is that even the management part is also getting changed, influenced by these changes. But we can skip that for now, and we can focus on the main part of it, which is the base station and the core part of it. So going to the next thing, a concept which I thought, which you might be aware of, but it's again good to keep it in mind, something called as access tracking specific and the non-access. And access, when you say it, is actually radio access. We are talking about the radio access part of it. So there are certain parts of this network which are very specific to the radio access, which is like saying that I can just say, take this diagram. So as part of the user equipment, the device, there are some set of modules, including the chips and the software, which are more related to, which are more working for the NR part of it. And they communicate with the access specific part of the base station. So this is kind of, they understand NR very well. There is another part which is non-access specific. It is irrespective of the radio technology. You don't look at radio here, radio part here. Same is with the core. So core is actually agnostic to the radio part of it. You don't look at what is the kind of access when you look at the functionality or the functioning of the core.
Excuse me, sir. What
Yeah.
do you mean by the non-access specific or access specific?
Sorry, can you repeat that, please?
What do you mean by the non-access specific or access specific?
Yeah, when I say access specific, it means that the functionalities here understand and cater to the access technology which is defined here. When you look at the 5G and where somebody asks you what is access technology, it is new radio, NR. When you look at the LTE, suppose you have an LTE device and the LTE base station E node B, the access technology is LTE. Similarly, you have a Wi-Fi access point, sorry, Wi-Fi device and a Wi-Fi access point here. The access technology is Wi-Fi. Or when you have wireline, you have a wireline device and a wireline, switches here. The access is the DSL example. So the access is where the device accesses the network, which is all this part of it, I call it. So this access is based on the technology that you use. In our case, if you look at each of the generation, 2G, 3G, 4G, 5G, you've seen clearly this technology is changing, right? From your GSM days to your CDMA, WCDMA to LTE to NR, this has changed, which means all these functionalities are changing. So they are based on the NR. So whatever design of this part is done, that is depending on the technology that you choose. Whereas a non-access specific is not depending on it. Even though you may have some information in this, for example, NAS would still know it is an NR connection, but the functionality of it, design doesn't change much based on the NR or LTE or Wi-Fi. So this, it becomes a something which is helping to make the common functions, we can say, common which is not depending on the NR or depending on the LTE type of access. They become the non-access specific part of it, which is the, I think this one mainly to understand is that the core network is non-access specific, whereas the base station access specific, and UE has both parts to cater to both. One part of it, of the modem, will be towards the base station. Another part of the modem is for talking to the core. And there are two distinct parts. We'll come to more details later on, but you can see there are two distinct parts in the UE, and G node B being the access specific node, first node in the network. They are more or less complete functionalities access specific, whereas the core is more or less complete functionalities non-access specific. And as I said, the access can be any of the things. So the advantage is that suppose you have another access specific node which is on 5G, let's say 5 access point itself. Now this is a 5G device, which is a Wi-Fi, and you have an access point, and we have some equivalent of a base station here, Wi-Fi equivalent of a base station, that can connect to the same 5G core. Because the 5G core is independent of whether it is Wi-Fi connection or NR connection. Almost all the functionalities of 5G core can be done through either NR or through Wi-Fi or through LTE also. So you'll also see in the later architectures that even the E node B can be connected to a new 5G core. The reason is that the 5G core is made as a access agnostic software or a system as such. So this is one concept which is good to understand in the overall level. Then,
yes, sir. So when you say access, are you referring to all the set of procedures we use like PRACH and ULSH transmission? So
exactly, yes.
Okay.
Yeah, they are all included in that. So when I say access specific, again, I'll come into details later on. It can be physical layer level, which is what you talked about, PRACH and say your PUSH and PDSH, those are the physical layer level. But there are also related ones on the top of it. You have all the logical channels, right?
Right.
So you have, so whether it can MAC level till radio level, layer 3, it can be there in the access specific. Because they all know exactly that you are working on an NR.
Okay.
So that is the design of those modules or stacks or components. Assume what is, or assume means it knows exactly what the technology is. It has to know, for example, OFDM is used, what kind of radio resource, kind of radio blocks are there. All that are known to beamforming is, if you look at massive MIMO, beamforming, they are all known to the access specific functionalities. But
Right.
your non-access specific don't even know, think about it. Non-access will not even look at MIMO. Non-access will not even look at your OFTM or modulations or your coding or rate matching. None of those will be known to a non-access part.
But what will it look at? What is the equivalent set of processes?
Yes, maybe we'll come to that. There are just two examples. I mean, one example, authentication of a user is something which is non-access specific.
Okay.
That doesn't need it need not be depending on whether it's going through NR or LT. So, for example, your SIM, you have a SIM and you have a ID in the SIM. That authentication of that ID happens at the non-access specific stratum.
Okay.
Example is that. We'll come to more detail because we'll cover this very in almost complete detail in the core session.
Okay. Okay.
Now coming to the various stacks and components in the these three of things, we can look at it from an OSC layer point of view. You know that the major ones are layer 1, layer 2, layer 3, and layer 1, layer 2, layer 3 all. Can I move this here? So they all happen to be defined, and they all work at a peer-to-peer level. So if you look at layer 1 talking to layer 1, layer 2 talking to layer 2, and layer 3 talking to layer 3. This is the typical ISO part of the 7-layer architecture. And layer 1 is called as 5, which is almost like synonymous physical layer. Layer 2, in our case, in the case of cellular system, and especially 5G, there are multiple sub-layers. So I just put the sub-layers. One is a MAC, which is again known to you. Is a media access part of it. Then there is an RLC, the radio link control. There is something called a PDCP, which is the packet data convergence protocol. And in 5G, there's a new one introduced called a SDAP. So these are all again, I would say, these three are again from 4G, but with slightly changed functionalities. SDAP primarily to look at the adaptation of the QoS. The service adaptation for the QoS was introduced as a SDAP adaptation protocol for the QoS part, which will come to again later on. So this is new. This part is new in 5G, and these three other layers were same as in 4G. So there are 4 sub-layers of layer 2 in UE, and similarly in same case with G node B also. And these are the access-specific ones. They don't come in the non-access specific. Is at the media access level, your link control level, and your primary some kind of a PDCP. If you just look at the functionalities, MAC looks at the HARC part, acknowledgements part. MAC looks at the scheduling part. 2-3 major functions I'm just projecting. So they form part of the MAC. MAC is also the one which actually converts all the logical information that comes from multiple places into the actual physical layer requirement, converting logical channels to physical channels. RLC is the radio link layer, so it has the acknowledgement the unacknowledged mode, acknowledged mode. It also takes care of segmentation. For example, if you have large packets and then the physical layer doesn't support large packets, you need to segment and then fragmentation and then defragment here. So those are the functionalities at RLC level. PDCP looks at the, in fact, there is 2 roles here. One is within a single node. It talks about how the ciphering is done, your header compression, they're all done on the PDCP level. And if you look at later on in the architectures, PDCP is where you can even have multiple, you can take data to another base station and the same base station. So PDCP is used for when you have multiple bearers or data traffic going through the same node or the different nodes. It's at the PDCP level that it actually diverges and converges. But this will come back to later on.
Here it's more like data channels and control channels, sir.
So that's a good question. Yeah, I thought I'll come to that later, but since you asked, I can answer. These modules are common to both data and control. MAC RLC PDCP does not distinguish between data and control in the sense of actually the role of it. But if you see that you'll be for control, you'll see a PDCP for control and PDCP for data. There are 2 different entities that will be in the actual G node B. 2 different instances of PDCP will be running, one for the control, one for the data. So your as the control channels will be through this, whereas your there is the data bearers will be like this, signaling bearers will be through the other PDCP. And same way you'll have RLCs also, and common MAC to take care of both, where it has to converge in terms of scheduling. You have to schedule all these control channels and data channels together into what a particular resource structure can be used. So that is taken care by the MAC.
Here lower layers, so layer 2 to layer 1, the physical layer that happens at the G node B or UE also. So the upper layers corresponds to the core, sir.
The core is only here. This is the core part of it. So these are all base station only. All these are part of base station, not only physical layer. And the base station, this is not be the base station, right? The base station has all these components: the layer 1 physical layer, layer 2, which including this SDAP, and then we not talked about it. The layer 3 is called RRC, radio resource control. So there is an RRC on both sides. So this is what the complete stack is inside a G node B and complete stack in a UE. So all the UEs in the world will have all these stacks. These are the access stacks, layer 1, layer 2, layer 3. And you have NAS also in UE, which corresponds to the NAS functions in the 5G core. There are multiple functions in 5G core, which takes care of the NAS functionality. Whereas in the UE, it's a single stack. That's why it's called just NAS stack here. It's not called a NAS stack here, but it's a NAS functions. And this is the kind of peer-to-peer logical connectivity between the NAS and the NAS. But actual data will always go through this way, all the way up to here. This is how it goes.
Sir, this SDAP is sometimes considered in layer 3 because I saw some diagram where it is drawn in parallel with RRC.
It is parallel with RRC. I'll come to that again later on. That part of layer 2 only. There is no confusion. SDAP is part of layer 2, but when you look at an architecture, if you look at the data channel, maybe I'll come to that later, then you can ask. Maybe clearer when I get to a few other diagrams where it clearly talks about how this SDAP is coming into picture.
Sir, what about the layer 1, layer 2, layer 3 in 5G core?
So there is no layer 1, layer 2, layer 3 5G core per se with respect to the whole system, because there is whatever is communicated from NAS to say the connectivity from 5G core to the base station is one connectivity, which is physical connectivity. The rest are for logical connectivity. And all these connectivity is using TCP/IP.
No, but
so there is no physical layer of 5G technology. There is no physical layer of 5G technology. That's what I was mentioning in the earlier thing about this access specific and non-access specific. So since there is no non-access, when access specific ones in 5G core doesn't care about the physical layer aspect. There are no 5G technology physical layer aspect which are in the core.
But how G node EV will communicate to 5G core without any physical media?
That is through TCP/IP. That's what I mentioned here. So the connectivity from G node B to 5G core is through TCP/IP IP connection, I would say. UDP is also there. Some are UDP, some are UDP. Yeah. It's an IP connection. So only if you look at the actual network, only the first part, maybe I can just go back just to show this. When I talked about this is a radio technology. All the rest of it now in all the new systems, let's not look at 3G. After 4G, later part generation of 4G and 5G onwards, all these are IP. All are IP networks. There is, I'll also come to that later on. It can be, when you talk about a UE, can have an Ethernet connection. That is not fully IP. But all the connectivity between the nodes, as I said, there are multiple base station nodes, multiple core nodes, all are connected through only IP. So it's almost like the PLMN network is based on IP.
Okay, sir, but even if I use the TCP/IP, it has got the layer 1, layer 2, layer 3. That you are not showing over there.
That it doesn't, the point is it's like any other IP network. Like when we have internet connectivity, yes, we don't care about what is a layer 1. So it can be any one of them, of fiber, it can have microwave, any of this can be used here. The whole 5G part of it is transparent to that. It's again back to the point I was talking about transport network here. The transport network can be any one of them. Partly it can be a ring, say for microwave, then fiber, then kind of say your
even satellite also.
Yeah, exactly. It can be satellite also. So any one of those can be used as long as it meets the basic performance requirements, both latency and throughput point of view. Any one of them can be used, and there are normally multiple hops. Any transport is, as I said, is very complex part of the overall network. though we don't look at it from a 5G engineer point of view, because that's a transport engineer's job. There are multiple technologies used during the transport where the base station is connected to the core.
Okay, sir.
So coming to now another concept, again, I think most of you could be aware, just maybe run through it, this question of user plane and control plane. And the user plane is something which we always know that it is basically to connect the user data. You have a user here, and the requirement of a 4G, 5G or any cellular network is to connect user to the corresponding network. So this is what we require. That's the basic purpose of any connectivity, any network as such. And that's what even 5G provides. And any component, node or functionality that does this, where it takes in the user input and then transmit all the way and delivers it. This is the user plane part of it. All the functionalities, all the components, all the functions and all the components that have a role in doing this form part of the control plane. And in the case of 5G, it's good to know one term called PDU session. I think earlier you must have heard of this in 4G. Who are familiar with 4G, there is something called a bearer. Bearer is a concept which is also there earlier, and this was quite used in the 4G technology called EPS bearer, radio bearer, and so on. So same bearer concept is extended in 5G and called a PDU session. A PDU session is like a pipe, the pipe that you see here. So a PDU session starts from the 5G entry, which is the first stack of the first component of 5G in the device, and exit at where it is delivered to the external network. PDU session extends from here to here. So what a 5G engineer, 5G network ensures is that this whatever data it enters into this pipe, into the PDU session, will be taken through all these components and then delivered at the exit point with the required quality of service. That is what it tries to do. And the type of such packets, in a way, when you look at a device, looks at it, is it an IP network or is it Ethernet network or something else? That is what defines a PDU session. So PDU session can be an IP. When you say PDU session can be an IP network, it means that the packets coming in are IP packets, and they are delivered as IP packets to the network outside here. Similarly, it can be in Ethernet. It can be an Ethernet session. If it's an Ethernet session, then Ethernet PDU session, it takes an Ethernet PDU packets here, not IP packets, Ethernet packets, layer 2 level, and delivers at layer 2 level here. And this is especially useful when you have an industry. Generally, all our devices are IP. We don't work on Ethernet level. But when you look at application of such systems in, say, industries, there are many such networks which are Ethernet based, which don't have IP, which have something else other than IP on top of it. So Ethernet connectivity is what the 5G has to ensure. And there's a third type called unstructured, which is none of the structured protocols, which is like an IoT equivalent. IoT, it is a kind of a random format that it may have to give, which means that the data that's coming in has no specific format. So the data as it is has to be picked up and delivered to the IoT servers or the whatever server is here in that format. So this is three types of PDU sessions which are there in 5G. In fact, these three were also there in 4G advanced. It was not there in 4G initially. IP was of course there. 4G was IP based completely. But these two came in 4G advanced release 13, 14 later on. But in 5G, it is inherently there. It is part of the basic network itself to have three types of PDU sessions. And also look at this network that is called data network or DN. It's the term that we will see being used occasionally. And the name of the network is called a DNN. So the this particular term you will see many a time in the 5G networks. Whenever it's a data network, it is any of the network that the 5G connects to or the network side, on the server side.
Sir, how the unstructured data is read then, because it has no particular structure, then how it is decoded or read?
Sorry, the voice was going down. Can you please repeat?
Sir, how the unstructured data is read then, because it has no particular structure, then how it is decoded and read?
Yeah, so it's a good question. Because it has no specific format of protocol, it has to be tunneled. So the in the device side, it could be possible because devices have its own ways of, say, for example, if you have an application here, an app can be, which is reading this data from sensors and then can put into the queue of the PDO session. But when you say here, how does it kind of give it to, suppose you have to give it to a server here, and since it's unstructured, how do you kind of send the data? So one of the ways is to have a tunnel here, an IP tunnel established between the endpoint of the 5G network to the server. So the unstructured data is passed through the tunnel to this server. There are also other functions which are specifically designed for this in 5G, where it can take from here as a packet, unstructured packet that is within 5G itself, and given to the IoT servers. So there are two types of such delivery of such unstructured data. Both are possible in 4G. Also, it was introduced late again as is in the advanced stages, and that has been adopted in 5G. Okay, so we just talked about the user plane. Again, coming to the control plane, all the control plane functions facilitate these user plane functions in order to carry the traffic from the user to the network and vice versa. So you will see that there are control plane functions in the user equipment or device. There are control plane functions in the base station and control plane functions 5G core. So there are specific or kind of very clearly distinct functions or control plane functions which are there in these devices. Similarly, you have the user plane functions also which are there in this. As I said earlier, when you look at this stack, these are the what they call the control plane functions. So you have NAS's control plane function, this is also control plane function, whereas the layer 2 and layer 1 don't distinguish between the control plane and user plane. As far as they are concerned, it's only bits. The information bits can be control plane information or user plane information. Only at the higher layer, SDAP is also one of those which specifically looks at user plane. It is not there for control plane, whereas all these functions are there for user plane and control plane. I'll show that in a kind of a end-to-end stack picture. So here it consists of all the stacks of the main 3 nodes. So this is the UE stack that you can see, the NAS stack and the complete layer 2 and the layer 1. Similarly, layer 1, layer 2 and layer 3 in G node B and the core part of it. If you look at the control plane, you can see that an application which wants to, it can either have a control information or sometimes may not directly have a control information. It may be generated from the device itself. This TE is called a terminal equipment. And for you to understand, this part is more or less the higher layers of the UE, the non-modem. This is the complete modem part of the UE, which is normally a single chip, like a Qualcomm chip or a MediaTek chip. And this is what runs on your the processor, whatever the Android and the application run on a processor. That is what is called as the higher layers. This is a distinction between the terminal equipment and the modem. And there is a fairly clear interface, but this interface is not a standard. It is defined by the equipment vendors or the chip vendors themselves. Like Qualcomm has its own interface like this, and then MediaTek has their own and so on. Samsung has their own and so on. So just to again understand the picture, we had talked only till NAS, but there are some software electronics above that, which is the what we kind of interface with. Your Android operating system comes here, all the networking as part of it, Android, which is like a complete operating system, like equivalent of Linux itself. And we have applications running on top of it. So applications interact with the operating system, which is part of the TE. They in turn interact with the modem. So there is certain layers which are defined in Android which can talk to the modem. So when you have a control function, for example, when phone comes up and wants to register, or you have a authentication to be done. So whenever the control function is given, the control function goes through NAS. NAS generates appropriate control signaling, goes through RRC, PDCP, RLC, MAC, and file. They get transferred to the base station. Again, goes all the way to MAC, RLC, PDCP, RRC. And some of the messages which may be only handled at the base station level, but if it is to go to the core level, it is sent through another interface called NG interface to the core. So this is what you see as a complete control plane path. But if you look at the user plane path, what you see is that the application data, your browse data, your voltage data, everything that comes from an application on the phone goes through the, of course, the networking stack of the layer, which is in this case Android, let's say Android, goes network stack of the Android, and that talks to the SDAP. SDAP, again, the same set of PDCP, RLC, MAC, goes to file layer, goes to the base station, goes all the way up to SDAP. SDAP in turn sends it to a tunnel, but we will come to that later on. It's called GTP tunnel, to the user plane function in the core. So now you'll see that I think the question was there earlier on SDAP functionality. SDAP is a layer 2, but it is I mean, it's just that it is above the PDCP, and that is the one which passes on the packet to UPF. So for user plane, there is no layer 3 inside the base station. Layer 3 is only IP, as we always seen like. So all the data packets go through the network layer, layer 2, PHY, layer 2, and to the UPF as such. So this gives an overall picture of how the different information packets run from UV to the core, and same way return also. Whenever something comes from the network, the UPF will direct it in case it's internet data or any data from the IMS or internet or any of the servers. They are directed to the NGU interface, which in turn sends to the specific base station. Base station will take it all to the layer. It knows exactly which user to send it to, and goes to the user. And since it is known, it goes to SDAP, appropriate IP address and application goes to the application. So this is another path. So what goes from the UV to the 5G core is called uplink, and what goes from the core or the network to the UV is called downlink. This is, I think, you are familiar with these terms anyway, downlink and uplink. So that's, I think, what it gives in terms of stacks. A quick look at the standard interfaces that are there, again defined by 3GPP. There is something called N1, which is a logical interface between the UV and the 5G core. And there is something called a N2, which is between the G node B and 5G core for the control plane part. This is a control plane interface. N3 is the user plane interface for between 5G core and G node B. And there is something called a N4 between the SMF, which is, I'll come to this in the later session. The session management function is the control plane function, and user plane function is user plane function. So this is between the control plane user plane protocol called the N4. And as a standard thing, this is a UU, which is the radio interface interface. So I would say these 1, 2, 3, 4, 5, and of course there is also one interface which is to the external called N6. So N1, N2, N3, N4, N6, and UU become the most important interoperable interfaces in 5G network. And this is something mandatory requirement for all the products in the world to cater to conform to, if they have to be accepted by the operators. There are a lot of other interfaces which I'll come to, but they are not that important for the interoperability part of it. So they could be.
Sir, where is the N5, sir? N5?
N5 actually is between the policy function. So that is again can be replaced by a new interface called a service-based interface. I'll come to that later on. So N5 is not required as a it's not a mandatory interoperable interface in 5G.
Okay.
So this is, I think, some information which again will be useful. We'll come to the RAN architectures. Maybe I'll try to complete this in a little slow. So I'll try to complete this and then we can take the session, close session. So RAN architecture, again, I was saying that earlier that RAN was fairly monolithic in the 3G world. In 4G also it was to start with, but later on moved to some level of distribution, especially on the radio side of it. But the extent of the cloud part of it came much later. The cloud RAN is something which was introduced much later into the 4G, and that is one of the starting points to look at the 5G architecture for RAN. In 5G architecture for RAN, there are mainly three components. It's a radio unit is one, which I think all of you are familiar, which is on the top of the tower, really transmits signals, analog signals. Then there's a distributed unit, as the name implies, it is distributed across, and there is a centralized unit. So there are three basic units in RAN. Now the question is, what is distributed, what is centralized? And that is a key question. And during the initial discussions of 5G in the 3GPP, a lot of options were considered. So you'll see that several options in the middle. And if you look at where to break the functionality, right from, if you look at RF, see the RF side is of course very clear. Then phi itself we can break into two parts. The lower part of phi, IA50 part of it can be lower part of phi. The high phi can be your coding and your rate matching and your scrambling, can be high phi. So there is one way to break it up. Second is MAC. MAC calls can be broken up. Where you have scheduling can be higher MAC, but your hierarchy is much more time sensitive, your frame sensitive. So slot sensitive has to be at the lower MAC. Similarly, RLC. RLC can also be broken up into, say, the segmentation can be in the higher one, but your acknowledgement and your actual packet formation can be in the lower RLC. So all these options we discussed. PDCP, sir. STAP is missing here, but I think you can just make it STAP also together here. They sit together. So that is not an issue. I think this is a standard picture which was there from this 3GPP TS838801. And this was before, this was in the initial stages. So at that time, the STAP was not actually finalized. So this breaking where you want to put the DU should be like option 4 means you have this complete set as DU. That is one way. Sorry, CU, and this can be a DU. Whereas if you look at another way, we can say option 5 means, option 6 means this part is high phi onwards is the DU, and all this becomes the CU. So a lot of discussion happened at various meetings. I would also say that there are other forums also where this discussion happened, in the small cell forum, in the open RAN forums. So there are other discussions which influenced perhaps what TGP was looking at. And finally, what they have mostly recommended is one option where the CU is here, right from option 2 onwards. And you have the something called an RU, which can you say is this part. Low phi and RF becomes your RU part of it, and the rest of it becomes the DU. That's what more or less has arrived at, but doesn't stop others from using other options. There are advantages and disadvantages of each of the options for various reasons, right from legacy to what is available in 4G and so on. They kind of now arrived at the most kind of agreed upon format is the CU is where you break at the RLC level. So PDCP, SDAP, RRC is in the CU, RLC, MAC, and high phi. The higher part of the phi is in DU, and RU is the lower part of phi in the RF. So RU, of course, sits on top of the tower, and DU could be hundreds of meters or even kilometer away from the RU, and CU or DU can be several kilometers apart. So again, a lot of important aspects are there, like what is written here. Where to split is also depending on what type of transport that you have. Because each of this, when you have CU, DU, there is a connectivity between RU and DU, connectivity between CU and DU. This, for example, is now being more or less standardized by Open RAN. ORAN part of it, not open, ORAN part of it. So, whereas this part, this interface, which is between the RLC and the PDCP, it is being defined by 3GPP. They already defined as a standard interface. So, we can have a DU from one party, CU from another party, and RU from a third party, and they should be theoretically be able to interoperate. It is still some time off before we can have commercial systems deployed in this fashion, which are interoperable, but that's an approach that's been taken. And there could be networks in near future where you may have CU and DU from two different vendors, which can interoperate through the standard interfaces. Yes.
Sir?
Yes.
So where does the FAPI interface come in here?
Yeah, so FAPI is actually driven by small cell forum, right? So FAPI has been defined in 4G between MAC and phi. This is the FAPI. So those who follow FAPI will try to partition here, where this can be a DU, this can be a CU. But I think the market is evolving, but I think this has not got much attention. This FAPI breakup, which was there specifically in 4G, especially for the small cell, it is not really so much caught up.
Right.
I think, in fact, now O-RAN split is now being more popular now. So it all evolves how the different vendors develop and which one becomes less problematic in implementation and so on. So it is still, I think, not clear exactly which all will succeed finally in the market. Which splits will succeed.
But FAPI is also a 5G concept, right? It's not only
Yes.
a 4G.
Now, they have kind of enhanced 4G into 5G FAPI now. So 5G FAPI is available, yes.
Right.
FAPI is available for NR, I would say. Because NR has a lot of changes, so all those have been accommodated, mostly accommodated in the 5G. Even FAPI is evolving in stages. The first version of FAPI was not so specific in their kind of what they have specified. It is not possible to interoperate with whatever they have written. But now they are specifying more and more so that it's possible to interoperate when you follow a FAPI specs.
Right.
Yeah.
Right. Thank you.
Yeah, I think there are several aspects to get into that. Maybe it's too less of a time, but I think the major idea was to show that there is a split which has this kind of what you call market and the technology-driven aspects, and some of them will succeed, but they will be primarily driven by standardization of interfaces, as I mentioned about this TCP standardizing here and Open RAN here, and other implementation-related things like your QoS. What is a load condition? So what is kind of transport available? If it's a transport here, then the kind of if you put starting from here, if the transport is here, then the extent of the throughput required on this is very, very high. Whereas if you transport your front haul is here, then your requirement is very less. So based on what kind of transport is available, what kind of functionalities are available in terms of slicing. You want to say this can also be put into, you can also look at, say, one slice has one slip, another slice, another split. So it is not that all base stations in the particular network should have the same split. You can have one base station having one split, another with another split. Even within same base station, you can have multiple splits. You can have multiple CUs and DUs where some DUs and some CU have a different combinations. So all those are practically possible. How much in the market we'll have to see, because all this costs, all these are development costs, and which of them will be kind of succeed. It is again based on how the RAN evolves. It is also kind of talked about there can be a dynamic way of slice kind of these changes can be done. Dynamic means it is not fixed. So at some time it is possible to change the role of the CU, where you can also take up additional part of the split can move from one to another based on the requirement. That is, I think, I would say a little far off. I don't see much of immediate product implementation coming with those things. So this is just to give another picture of the same thing, where you have the radio units, which are actually at the tower. These are the tower and the cell locations. And you have that DU connectivity can be few hundreds of meters to several kilometers. And this can be, this is again what is called the front haul. We call this as front haul. And this is a mid haul. And the CU to that core, this is the back haul. This is a core, this is a back haul. This is how the market calls these different transport connectivity networks. So the connectivity here has a different requirement with the connectivity here and so on with here. So the latency, the throughput, I think whoever has developed or looking at O-RAN would really understand the complexity of this particular front haul. And based on the split that we adopt, the mid haul requirements change. Whereas the back haul is something which is a standard. We talk about primarily in terms of how many CUs connect to the core, as we discussed earlier. The back haul and where all they are distributed, because the same CUs are in multiple places. How you connect all of them to the core is another transport network architecture problem. And we can say that now the question of what is a G node B? This is a G node B. This is I think I want to ask a question initially. So G node B is not just CU. G node B is not at RRC. G node B is not just baseband. G node B is not just RU. All this together become what is called a G node B. So that way G node B becomes has a much bigger kind of meaning to brings a different meaning to a base station in 5G than what was earlier. When we think of base station, you think of a tower and a kind of an electronic box, but it is much more than that, where a G node B can be itself covering several square kilometers and tens of square kilometers. This last slide for today, this we can close. Again, as I said, there are some standard interfaces which are defined by 3GPP. So between a DU and a CU, there is something called F1. F1 for control plane, F1 for user plane. And since we have the split for the control plane and the user plane, we have a G node B central unit control plane, G node B central unit user plane. And as I mentioned earlier, DU may not have CP and UP separately because mostly they are L2. Here we have L3, and you may have PDCP and desktop. Similarly, you have a PDCP and desktop for the data part of it. These are the various interfaces. There is an even defined. Even is another interface defined between the control plane and the user plane function of the CU. So that forms all the intra G node B interfaces. And for the inter G node B, this is one G node B as you mentioned earlier. If there is another G node B here, which is similar structure or a different breakup, this interface between the G node Bs is called XN. Is again a new interface. It was X2, which was called in LTE area, LTE times. Now it is called XN, the next generation XN. So XN is another interface which is defined between the G node Bs. And XN can have both control as well as user plane. So that is, I think with that we can close. I think though we thought of coexistence, maybe we can take it in the next session. I think the time is up also, I feel. So any other?
Okay. Thank you, sir. Thank you. Thank you.
Yeah. So if you have anything specific questions, you can even send it offline. I'll try to answer that.
Okay.
Okay. Thank you, Emerson.
Okay, then I will. If there are no questions, I'll probably we can all sign off. For Saturday, I will try and supply another link. So
Sure.
in case Professor Ganti cannot make it to the call, there won't be any confusion as there was
Sure.
today.
Yes.
So again, thanks everyone for attending the call, and thanks Babu sir for talking about 5G core and whatnot. So the next class will be on Saturday, the same timings as usual. So please attend that as well.
It's at 9:30, Nabilan?
Yes.
Okay, sure.
Yeah. Okay. Thank you all. See you.
Thank you.
Have a good day.
Thank you.